All right, so now that we finished section 4.1, and here's the homework that went with it. And I cover 4.1 and 4.2 in one day, so I'm going to continue with this. You should have received two handouts. I mean, one of the groups you're still coming in, and I'm having to give you these handouts yet. Today is Monday, so tomorrow, Tuesday, you'll be writing this anyways. You'll be writing the test, so then I'll be giving you these two handouts. But everybody else, these two handouts we're gonna need for these notes here. Okay, so we're gonna start talking about 4.2 irrational numbers. So you have to know the difference between rational and irrational numbers. Okay, so let's go ahead and write down the notes and have those two handouts ready as well. So rational numbers they can be written as a fraction. Can be written as a fraction in the form m over n, where m and n are integers. Okay, that's the definition of rational numbers. And sometimes if you have a hard time differentiating between the two, it's maybe best to just focus on what is an irrational number. That's the one I'm going to give you next, right? But I'm going to give you some examples of rational numbers and how else you can identify them. If you determine the decimal, right, their decimal representation either ends, it's finite, right, it stops, or repeats indefinitely. Okay, so examples, 5 would definitely, like whole integers are definitely all rational numbers. 3.25, that ends, right? Negative 64.3, it ends, right? You can tell that it ends here, so definitely a rational number. 4 over 5, would that be a rational? That actually turns out to be 0.8. So first of all, it can be written as a fraction. That right away tells you that it is a rational. But if that wasn't enough, right, you go to the decimal, you turn that into a decimal, you also see that it ends. It doesn't keep going indefinitely on your calculator, right? Even though you're not allowed calculators in this unit, you will be able to use it for the trig unit, which is after, and the measurement. And then what about negative 77 over 100? Well, first of all, yes, it's written already as a fraction, but if you wanted to take it further, if you turn that into a decimal, which is easily done, right? The decimal shifts two places to the left. That's negative 0.77. So it ends. It doesn't matter if it's positive or negative. What about 1/3? Well, yes, it can be written as a fraction, and it's also 0.33, and it keeps going, right? Like it just keeps going indefinitely, so it's also rational. What about the square root of 81? Well, let's see. You get 9, right? So if you get a whole, like an integer, a whole number, you're also guaranteed, because you can also think of it as 9.0, right? It ends, right? It doesn't keep going. 2/3, right? First of all, you can write it as a fraction, so right there, it meets the criteria, and it also keeps going, right? Indefinitely repeats, it doesn't end. Another way of looking at 9, for example, or any one of these integers, can you write 5 as a fraction? Yeah, it's 5/1, right? So these are just few examples. There's many more that would be considered a rational number. So these are just some examples there for you to look at, okay? And we're going to fill out that form as well. So irrational numbers. How will you identify them? Can't be written as a fraction. Cannot be written as a fraction. And another way is decimal representation neither repeats nor ends. So it doesn't repeat or end, and that's how you know. And I will just say continues to change indefinitely. And so when it changes, there's not even a pattern, because sometimes there are decimals that repeat, like 0.14, 14, 14. Like that's actually a repeating pattern that would be under this scenario up here. But irrational numbers, it doesn't even have a pattern. There's no pattern to it. So pi is a classic example of an irrational number. Okay, so some examples here. The square root of 17 would be considered irrational. So if you use your calculator for that, this is what you get, and it keeps going. So that would definitely be considered an irrational number. The cube root of 4, pardon, is 1.58740, and that keeps going, right? Pi, what is pi? That's 3.14159, and that keeps going, right? The square root of, or the fourth root of 2 is 1.41421, and it keeps going, right? So that's those are all examples of. So to continue this, so when you have roots, right? If the index of the root, if the index of the root can't be canceled out, can't be canceled with the power of the base, right? It will be an irrational number. Okay, so that's another thing that you can tell right away, right? Like, for example, this is a square root, right? Is there any way that you can write 17 to the power of 2, or like break this down so that you have a prime factor to the power of 2, so that you could cancel out the root, the index here? No, there's no way, right? So you could continue this list, right? You could make up, right, the fifth root of 4, right? There's no way you can write 4 as factors where you have 2 to the power of 5, right? There's no way. So there you know already if it's not a perfect, right? Like square roots, you would have to have a perfect square in there. Cube root, you would have to have the perfect cube in there, and so forth, so that you could actually cancel out the index, right? The whole root with the power, and that's how you know whether or not it is, right? So we'll do some examples here, right? Classify the following as rational or irrational. And we'll kind of learn how to do this. Just like with the factoring, right? We have to kind of go through which one is a PST, which one is a DOS, which one required the matrix, right? You have to kind of navigate through, right? And so let's say you have cube root of 26, let's say, right? And then, so we're asking you, is this rational or irrational? Explain, right? Well, 26 is not a perfect cube, right? Notice that the index of this root is 3, so you need it to be perfect cube, right? 26 is not a perfect cube. 27 would be, because that's 3 times 3 times 3, but 26 isn't, right? And just to make sure you understand, decimal form is, and I'm just going to take the cube root of 26 here for you to see. It's 2.96249, right? It repeats, no pattern, right? It keeps going, that therefore irrational. You could have stopped already at this. Like if it doesn't meet the first criteria there, you're done. Okay, B, how about square root of 16 over 25? Right? That actually, right, you can actually take the square root of 16 and the square root of 25 separately like that, and that is 4 over 5. Can be written as a fraction. Therefore rational. Notice that there are no roots left, so they were both perfect squares. I'll make a note, both perfect squares. Because in this case, your index was 2, right? So that's how you identify it there. Okay, continue. C. What if you had negative 1.21? And D. What if you had negative square root of 4 over 10? Take a moment and see if you could identify that. Okay, so here, we need to be able to write it as a fraction. We can't really, right? Like we could have done that. You could write that as a fraction by just going 121 over 100. So check, that be rational, right? Can be written, can write as fraction. That would be the first check, right? Or, right, decimal terminates. Terminator, right? Think of the Terminator, right? If it terminates, it's therefore it's rational. It doesn't need to, you don't need to show both. You just need to stick with one. Here, right? 4 and 10, neither one, right? 4 nor 10 are perfect squares, therefore irrational. Like there's no, if you can't cancel out the root somehow, if you can get rid of it, then it's irrational, right? So there you have it. Let's keep going a little bit more. Let's try some ordering again. Order from least, sorry, in ascending order. Okay, so let's say I gave you cube root of 13, root of 18, root of 9, and cube root of -5. Let's say I asked you to arrange this in ascending order, so from smallest to greatest. So go ahead and do this right now as part of, I already did this on the previous lesson, the first lesson that I posted. If you need a review, go and review that there, but see if you can arrange this in ascending order. Pause it and then do that. All right, so what I do is I look at the index, right? And then, so this one you're looking for perfect cubes close to it, right? So the perfect cube closest to them, right, would be if you go 2 times 2 times 2, so 2 cubed would give me 8, and 3, which is next on the number line, right? 2 cubed would give me 8, 3 cubed would give me 27. So the two perfect cubes that are where this radicand is found between is between 8 and 27. Okay, and so you have to kind of understand, right, that this would be closer to here, right, closest to this value here, to the 8, right? So if you think of between 8 and 27, there is almost 20 difference, right? So this would be 18 right about in the middle, so we're thinking 13 should be somewhere in there. Okay, so knowing that the cube root of 8 would be 2 and the cube root of 27 would be 3, this one here we can say the estimating, right, we get approximately 2 let's say 2.3 or something like that. Okay, 2.3 is what I'm going to put down. That's good, close enough, right? Here we're thinking the index, right? We're thinking perfect squares, right? I'm going to keep that here. And so you do a number line, right? And you try to find the perfect squares that this number falls in between. So 3 times 3 is 9. 4 times 4 is 16. So 16 is the one that is below 18. 5 times 5 is 25, right? So 18 is between 16 and 25. So 18 falls right there. The square root of 18 will be approximately, sorry, squiggly, 4.3 or something like that, right? So you kind of estimate that 4.2, 4.3, that's close enough. We're not asking for you to be exact, just to estimate using this method. Then you have another index of 2, so you're looking for square roots as well, right? Perfect squares. Perfect squares. And you have 2 squared would be 4. Oh, actually, never mind. Why am I doing this, right? There's no need to do this. That's exactly 3. We know exactly 3, right? And then this one here, this is the one I was looking at, right? Cube root of -5. So here you have to be careful. You can always take the root of a negative number, provided that it's an odd, right? Odd index. Right? Can take root of negative. Okay? So that's not out of the question, but that can be done. So think of this, now you want to go to the negative in the number line system, right? So 2 cubed, so 2 times 2 times 2 would get you to -8, right? And then 1 cubed would get you to -1. -1 cubed, right? So you have to think of the negative number line here, because anything with an odd power will give you a negative. If you take a negative and it's an odd power, so 3, 5, 7, and so forth, you'll always end up with a negative. So this is -2 cubed is -2 times -2 times -2, right? That's -8. And so -1 cubed is just -1. So that's your number line here that we're zooming in on. -5 would be right about there. There's about 7 of a difference here. 4.5, yeah, that's about right there. So the cube root of -8 would be -2. The cube root of -1 would be -1, right? So the cube root of -5 would be approximately, I'm thinking, negative 1.8 or something like that. And sometimes if you're not 100% sure, it's not even crucial, it's not critical, because this is a negative value, right? These are all positive. So you know that this value, no matter what, is going to be your lowest. And then you look at these numbers here, this 2.3 here, so cube root of 13 is the next after, right? If you go from lowest to greatest, then you have square root of 9, and last you have square root of 18. And so now you have arranged it, right? This is the smallest, and then comes this, and then this, and then that, right? So that's how you arrange it. One more example here. Okay, so let me give you the homework that goes with this. But before that, I would like you to fill in that green handout that I gave you, just to have an overview of the number system. Okay, so this is the number system here, and you can take that green handout and write in these values here. And I would encourage you to start from the small box where we have the natural numbers, and it starts from 1, 2, 3. So before you write this down, just listen to what I'm saying here, right? Natural numbers are all whole numbers starting at 1, right? Then you have the whole numbers themselves, which is you add the 0 to it. Okay? Integers would be basically they keep on expanding, right? You add the 0 here. Integers would include negative whole numbers as well. And notice that, right, within the integers, you have the natural and the whole numbers, right? And then the rational number system, right? The rational numbers encompass all of these subsets here that you have here. So rational numbers are any number that can be written as a fraction or has a decimal that repeats or is finite or terminates, right? That's how you know you have a rational number. Negative, positive, it doesn't really matter. Okay? Irrational, right? Here you have a few examples, and it's basically when you cannot write the radicand, right, in such a way that you can cancel out the root. Then you know you have an irrational number, right? And imaginary, if you'd like to imagine, right? There's actually in the higher grades and pre-cal, you do deal with imaginary numbers. We don't. So don't worry about it until then. And I also have the summary of what we just wrote down again down here, so that you can you have something to go by. It's all summarized in one place. So if you want to pause it and just write this down, you go for it. I am going to ask you to work on, I'll give you the homework here. I'm just going to see what I already gave you from So here's page 211. 3, 4, 8, 10, 11, 12, 14, 15, and the handout. And the handout I'm talking about, and it's a double. Okay, so you have that. And it's the same thing again down here. So disregard that. And basically what you're doing here, classifying all of these numbers as natural, whole, integer, rational, irrational, and so forth. Focus on just these two here. Okay. And the rest, you can basically place every number within a multitude of categories, but sometimes you can narrow it down to just one of them. But I would like you to just differentiate between these two, okay? That's it for this video. I will have to post one more tomorrow, okay?